Okay, so welcome everyone back. Today we are very happy to have Petr Horava, who is going to tell us about topological quantum gravity of the Ricci flow. Thanks for joining us.
Great, thank you very much. Thank you for inviting me. This should be fun, at least for me. And I appreciate the correct pronunciation of my name from Mirek, who of course speaks the same language. So this is a rare opportunity. He could have done the introductions in Czech, but then I would be the only one besides him who understands. So I think this was just perfect. Okay, so I'll be discussing a new subject, something that is based on some recent work that we finally published in a sequence of 3 papers last year. There's also some follow-up that we are working on, so there'll be definitely more interesting results. And we are kind of hoping that we can invite others to join the effort, both on the physics side and on the mathematical side. So in that sense, I feel like the subject of how do you formulate a quantum field theory for gravity of the Ricci flow equations? It's a subject that perfectly fits the interface between physics and math. So I don't feel too guilty to talking about it in this particular seminar. So this is based on, as I said, work done recently over the past few years with 2 of my students, Alex Frankel, who was an undergraduate in Berkeley, now he's a graduate student at Stanford, and Stephen Randall, who is my graduate student finishing this year. I believe Stephen is checked in for this meeting as well, so maybe you can direct some of the more difficult questions towards him. And the 3 papers are listed here, so I'm not going to read the titles. They're all an attempt to break into a new direction, connect 3 previously unrelated topics in physics and math. So let me see if I can actually explain the 3 topics in some kind of a lightning overview. I know that many of you are experts on some of the 3, if not all 3 of these topics, but since it's a mixed audience, I'll try to be sufficiently broad instead of jumping to technicalities right away. So I don't want to lose most of the audience by omitting some of the background. So the 3 topics that we want to connect are topological quantum field theory. So our framework will be using the language of path integrals for quantum fields. And the topological quantum field theory, there are many different ways of defining what you mean by topological quantum field theory. Different people might have different criteria what topological means. Some people would say it means independent of a spacetime geometry and spacetime metric. I would say the primary point is that topological field theories will have no local propagating degrees of freedom. So all of the information about interesting correlation functions that come out of the path integral will be keeping track of global issues in global geometry. But our topological quantum field theory will not be a theory of Yang-Mills gauge connections, which is probably the most famous, most understood, best understood example of topological field theories. It will be a theory of quantum gravity. So it will end up depending on the background geometry associated with the Riemannian metric, and in some sense makes connection to the theory of Ricci flows, as we will see later. So what is the mathematics of the Ricci flows? Again, some of you are true experts on this field. It's a fascinating, still very dramatically expanding subfield of mathematics. It was essentially originated by Hamilton in the 1980s as an attempt to provide new tools for understanding the geometry of manifolds and perhaps attacking some of the deep conjectures in geometry. And that progress on that field of using the Ricci flow of a Riemannian metric to understand geometry progressed relatively slowly until, of course, the big revolution arrived at the beginning of the 21st century when Ricci Perelman reformulated the theory of the Ricci flow slightly, added a few more ingredients, and used it famously for proving the Poincare conjecture. And since then, of course, many other useful results have been accumulated, and I'll comment on some of that later, but I'm certainly not an expert on this point number 2 on my 3-point transparency. The third point here that we'll be connecting is the theory of nonrelativistic quantum gravity, specifically of the Lifshitz type, which of the 3 subjects, it's the youngest one but there have already been thousands of papers written on it also since 2008 when this new approach to quantum gravity was initiated. The motivation there was to see if we can still get away with using old-fashioned quantum field theory methods, path integrals, local fields, in order to understand quantum gravity beyond the regime of low-energy effective field theory. And it turns out that if you temporarily abandon Lorentz invariance, you can broaden the spectrum of gravity theories in a very interesting way. Whether or not that's relevant for describing gravity in our own universe is still an open question, but this issue of non-relativistic gravity has already provided lots of interesting spin-off results, including holographic duals for various non-relativistic quantum field theories, building on the famous ADS-CFT correspondence and pushing it into the non-relativistic regime. And we are learning many new surprising twists and turns that come out of this idea of abandoning Lorentz invariance as a fundamental symmetry. It opens up new doors and hopefully will provide new tricks how to attack the hierarchy problems in nature. However, today I'll be interested mostly in purely mathematical applications of this non-relativistic gravity. I will not be asking how to make this non-relativistic gravity somehow magically consistent with the real world. I'll be instead asking whether we can formulate a topological version of this non-relativistic gravity defined in the old-fashioned sense, following in Witten's original footsteps, defining a BRST charge for topological symmetries, constructing a Lagrangian, such that the localization theorem for the Lagrangian in the path integral of this theory will localize us to the solutions of the Hamilton-Perelman Ricci flow equations. So that seems like a worthy task from both sides. You could expect that in principle, this could teach us something more about Ricci flows by providing this perhaps unexpected connection to a full quantum theory of gravity. But it can also teach us some of the lessons that we are searching for on the quantum gravity side, on the physics side, because there's been so much progress made over the past 2 decades on the mathematics of the Ricci flows. I'm fascinated by the wealth of data and information. Many textbooks have been written on the subject and many beautiful results have been established. And now in principle, if we build this bridge to quantum field theory, we can try to borrow these results from the mathematical side and import them into the quantum theory side and see what kind of new lessons this might teach us about quantum gravity, even though it will be in this topological regime where we do not have propagating local graviton degrees of freedom. It could still teach us more about, for example, short distance completeness, ultraviolet behavior, the form in which the localization allows us to evaluate the path integral in the presence of topology changing processes and so on. So that's the hope, that this direction, once established, can be tested as potentially being useful in both directions. So let me begin on the more mathematical side as a reminder to those of you who perhaps have not seen Ricci flows before. Hamilton's original Ricci flow is formulated for a spatial metric Gij. I'll be using what I would call, in a fancy language, the Penrose abstract index notation. So objects that you'll see in today's talk, they will look like they're written in coordinates, but they're really, the indices here are there in the abstract sense to remind us what kind of tensors these objects are. So I'm not necessarily in coordinates, even though I'm using this pedestrian notation often to make sure that everybody's on the same page. I don't want to flood you with some abstract notation. So this Gij is a metric on a spatial manifold parameterized by some coordinates xk. So the spatial manifold sigma is of some dimension capital D. So capital D will be an important parameter. I'll be trying to construct the theory formally as a path integral quantum theory in any number of dimensions. But of course, the most interesting case will be the case where D is equal to 3, which is both fascinating physically and also happens to be the case where most information is available on the mathematical side. So if you allow this metric on space to depend on a time dimension, you can postulate a flow equation. This is Hamilton's original flow equation. Not a very great equation. It's fascinating, but it does not have some of the nice properties that you would like. For example, the right-hand side of the equation does not follow from the variational principle. And that's a shame because we like variational principles. So what happened 20 years later, after Perelman's pioneering work, he modified the Ricci flow equations by adding, besides the spatial metric Gij, also a scalar object phi. He called it the dilaton. The terminology was inspired from string theory, but I'll comment in surprising ways, perhaps. For those of you who haven't seen our papers, you'll be surprised that we'll find a physical role for this field phi in a completely different corner of our physical theory. But we can refer to it as Perelman's dilaton for now. So there is now a combined set of equations. The dot, the over dot on all objects will always refer to a time derivative. So it's a shorthand for this object here. And you have now a coupled set of equations. They look slightly more complicated, but they have also nicer properties. They follow from a variational principle. Essentially, you vary a very simple functional, which also for Perelman was inspired from string theory. It would be kind of analogous to the string worldsheet approach to the beta function equations and then the space-time effective action in string theory. But the motivation from string theory is tangential. I'm not going to rely on it at all. We'll develop a completely different connection to physics, not the one that Perelman was originally potentially inspired by. So in order to connect these two equations, what you can do is to perform a simple trick. You can apply a diffeomorphism to this equation, to set of equations, which is generated by a gradient of the field phi itself. And if you do so, you're performing the so-called de Turck's trick, which, by the way, was originally developed in Berkeley. I think de Turck was at MSRI when he did this work. And you nicely decouple the original Hamilton equation here, the flow equation, from some slightly funny-looking flow equation or inverse flow equation for the scalar field phi. So this would be one step that we need to somehow look for when we try to embed this into the physical setting of a path integral. We'll look not only for localization to the Perelman-Ritchie flow, where does it originate? How can you accomplish it in a context of topological quantum field theory? But we'll also look for the opportunity to allow ourselves to perform things like this de Turck trick. So we will expect, for example, the diffeomorphisms of space should be allowed to be gauge symmetries in the sense of being allowed to depend on both space and time. So we'll start with a primitive version of the theory first. I'll construct the simplest possible theory of topological quantum gravity, which has something to do with some kind of a Ricci flow. We'll find out that that Ricci flow in the simplest possible theory is precisely Hamilton's Ricci flow and its generalizations. So we'll be finally somewhat remedying the old objection that the Hamilton-Ricci flow does not follow from the variational principle. We will still not derive it from a variational principle, but we'll see it as emerging as the localization equation from a Lagrangian in a d plus one-dimensional quantum theory of gravity, which happens to be non-relativistic. And then I'll try to add more and more gauge symmetries, including spatial diffeomorphisms and what else might be interesting to add. And we'll see how the story will develop to incorporate the more complex set of Ricci flow equations due to Perelman. We'll find a role for the dilaton, and we'll zoom in on that particular corner of the space of coupling constants in the topological gravity, where precisely Perelman's equations show up. So that's the plan. This is just a comment on the previous transparency. There are two more, at least, technicalities that we'll have to encounter in the construction of this topological quantum gravity. We'll have to look for the role that Perelman's F functional plays. This is the functional that I was mentioning earlier that you use in order to derive the right-hand side of the equations from the variational principle. By the way, this has always been very puzzling to me. Why? Maybe this is a sociological question that some of you might have an answer to. Why do people, including Perelman originally, obsess so much about deriving the right-hand side only from the variational principle, but they don't really care about where the left-hand side comes from? But in any case, you'll see how both sides of the equation, in our case, follow from the localization aspects of the variational principle in the full non-relativistic d plus one-dimensional theory. But there is a d-dimensional functional defined on space, defined through this way. Again, string theorists would recognize in this some rudimentary features of the space-time effective action. That connection, forget about it for now, we'll be providing a different connection. So one technical issue is, where is in our topological quantum gravity Perelman's F functional? What role does it play? The second, and perhaps even more challenging question will be, in order for Perelman to derive those equations that he was interested in, he was imposing somewhat, from my naive point of view, an ad hoc condition, a fixing of the volume element. So it defines a particular combination of the dilaton, the exponential of the minus the dilaton times the standard Riemannian volume element on the manifold, and keeps that fixed. So this can be an arbitrary measure on space. It does not, there is no prescription for how the spatial dependence should look. There's only the condition that it should be independent of time. So how do you possibly get such a strange condition dynamically out of topological quantum gravity? So that will be one of the challenges, and hopefully we'll be able to see the clear answer. We do have the right answer, I believe, and it came as a slight surprise. I was expecting at first that perhaps such a condition will have to be imposed as a partial gauge fixing, where you reduce some of the diffeomorphism symmetry and end up with a theory which requires additional gauge fixing of the remaining part of the gauge symmetries, but that's not what we found. We actually found a dynamical limit where this equation automatically comes out of the dynamics of non-relativistic quantum gravity. So hopefully this will be clear by the end of my talk, and it's one of the highlights of the story, in my opinion. So again, this is what you call it, bringing coal to Newcastle, or the Czechs would say bringing wood to the forest. As well, I don't want to get into discussions in Czech, but in any case, I don't have to remind you guys, some of you, as I'm looking at the list of people who are participating, are among the people who have significantly contributed to these developments. Over the past 20 years, an amazing wealth of data has been accumulated, and I'm very much eager to see how some of the results and some of the theoretical notions, many notions of entropy that play a role, the understanding of space-time singularities, topology change, Ritchie flows with surgery, all these issues should have some kind of a meaning and implementation in the context of the quantum gravity path integral. So this might be one of the very few places where the mathematicians have already provided for us many of the answers through theorems, which are of course not phrased in the physics language, but if we only translate them to the language of the path integral, we might be for the first time perhaps learning about some of these very complicated expected processes in quantum gravity, such as topology changing amplitudes and various space-time singularities that can develop. Okay, so to be even more elementary, let me give you, or those of you who have not experienced Ritchie flows before, this is more of a physics transparency, the mathematicians don't need it. Just 3 quick pointers what to expect generically from these Ritchie flows. First of all, the Ritchie flow is usually set up as an initial value problem. You start with some initial configuration, you let it go and observe what happens. So already that will be different compared to what we are interested in, let's say, topological Yang-Mills gauge theories, right? In topological Yang-Mills gauge theories, we are in a relativistic 4-dimensional Euclidean signature geometry, and we are interested in some intersection numbers of some non-trivial cohomology classes, Donaldson invariants, moduli spaces of instantons on which these universal cohomology classes reside. Here, the focus will probably be different. We will be more interested in reformulating the initial value problem in quantum gravity, questions about the wave function of the universe, things of that nature. So even just to sort out the question of what are the correct correlation functions and observables, that will be an interesting challenge. But leaving that aside, let's just go back to the classical Ritchie flow. I start with some initial configuration and let it go. And of course, there are now theorems that tell you not only that the solution exists for some amount of time, but also once you hit a singularity of a certain type, especially in 3+1 dimensions, my understanding is that all possibilities of what can happen are in principle classified. So that's a fascinating insight from the mathematical side, which I'll be trying to combine with physics. And so if you start with a flat manifold sigma, of course, it just stays there forever, it doesn't change. If you start with something which is a, let's say, a slightly deformed sphere of positive curvature, and here I'm using examples specifically in 3+1 dimensions, just to be clear. If you start with a somewhat deformed 3 sphere, you let it go, then two things happen. First, it starts rounding itself, and then eventually it collapses into a singularity in such a way that the entire sphere collapses at one instant in time. So that's a nice kind of uniformization of the evolution of the sphere. If you have something that's hyperbolic, then it will, of course, then expand forever. So those are some very simple examples just to make sure that we are all on the same page. If I set up a slightly more complicated example, so this is, again, the initial condition here at early times. I should have said that time in my drawings always goes from the bottom up on each transparency. So I start with some initial three-dimensional configuration, which is a more deformed sphere. It might be of this dumbbell shape. So what happens is that, of course, these positively curved regions, they'll behave as if they were just regular 3 spheres. So those regions will be rounding themselves to be more and more round and eventually collapse to a point. But the bridge between them develops a neck, which causes in some finite time t sub s a singularity. So of course, in the early stages of the theory of the Ritchie flow, this was dealt by performing surgery on the manifold. So you zoom in on just before you reach this singularity, and the geometry has roughly the shape of S2 cross an interval. And as the interval is being pinched away, what happens is that you decide by hand to replace this geometry at Ts minus epsilon with a new geometry Ts plus epsilon, where you have performed surgery replacing the original S2 cross an interval with two three-dimensional disks. And then you reset the evolution and you follow this through. Now, my understanding is that in recent, semi-recent papers within the past few years, people like Richard Bandler, who I believe is in the audience, have managed to improve significantly on this surgery, and they can actually now follow through the singularity in a much more controlled way without having to perform this kind of epsilon procedure. But again, I'm no expert by any means on this subject. I'm just observing this and being fascinated by the mathematical structures that are being found, especially in those dimensions of interest like 3+1. So when you're performing this surgery, there is a universal model of the singularity, of this neck pinch singularity. It again goes through several steps. You find a way in which you can zoom in on a shorter and shorter distance behavior. This is what comes naturally to a physicist. I would call it a renormalization group procedure, where you step by step zoom in on shorter and shorter scales. And then as you are performing this procedure, what happens is that the transverse dimension here becomes essentially a spectator, and the neck pinch singularity can be modeled simply by an S2 two-sphere collapsing to a point, while the third dimension of space is being just a translational invariant spectator. So this is the type of procedure that mathematicians would perform, and it has definitely a very deep renormalization group smell to it. So we can ask similar questions later on when we develop a path integral for this quantum theory of gravity. We can ask physics motivated questions. What happens when you zoom in on some short distance regime in the theory? What kind of behavior can you get? Do you understand the completion of the physics of that topological field theory at short scales, or do you need some additional degrees of freedom? And I believe that the answer, to kind of spoil the punchline, the answer, at least in 3+1 dimensions, will be that we can indeed just borrow these beautiful results from the mathematical literature and claim that despite all expectations, this topological quantum gravity theory as a physical theory is short distance complete. It does not require any new additional degrees of freedom to be made sense of as a physical theory. So I'll comment on that at the end. So now that I've reviewed at least some naive highlights of the theory of the Ritchie flow on the mathematical side, let me tell you some background about non-relativistic quantum gravity, or as I call it, gravity with anisotropic scaling. Many of you who've dealt with Ritchie flows already know that the Ritchie flow treats the scaling of space versus time anisotropically. There is a certain way in which if you rescale lengths of space by a constant parameter lambda, you are better off, better adjusted to the nature of the theory by rescaling time, not by the same scale lambda, but a lambda to the power of 2. In other words, the Ritchie flow exhibits anisotropic scaling characterized by what a physicist would call dynamical critical exponent z equal to 2. In physics, there are many systems, especially in condensed matter and in non-equilibrium physics, where this dynamical critical exponent dynamically it is not equal to some naive values 1 or 2. It can have all kinds of other fascinating values. And it does not make sense to me to stop ourselves from importing this important quantity, the dynamical critical exponent, into quantum gravity. If you insist on quantum gravity being described fully relativistically, so you're trying to quantize standard general relativity, what that means is you're postulating that the dynamical critical exponent in your theory, since the theory is relativistic, it has to deal with space and time on the same footing as far as the scaling properties of the theory. You're declaring from the get-go that the dynamical exponent is 1. But what we asked some 14 years ago is what happens if we allow ourselves purely mathematically this more general situation where we do assume some form of anisotropy between time and space. We can certainly formulate a mathematical theory of a fluctuating geometry metric on this foliated space-time manifold where time has a different role than space. And we can study whether dynamical scaling exponent than 1, for example 2, as is relevant for the Ritchie flow, whether they can make physical or mathematical sense. And I think you've heard my cat, he always meows when he hears about anisotropic scaling. So maybe he's going to be contributing more. The more I talk about z not being equal to 1, makes him somehow want to be heard. A very elementary example, and if you are not interested in listening to this example, you can take a 2-minute break from the talk, but just to show you, for those of you who are familiar with just elementary path integrals in quantum field theory, there is a very easy example of a system with a z equal to 2 anisotropic scaling. It would be a quantum field theory of a scalar field phi, which is a function of time and space in some number of spatial dimensions d. And I'm postulating a free Lagrangian, which has a kinetic term with 2 time derivatives and a potential, spatial derivative dependent term, often referred to as the potential term in this context, which is a 4th order in spatial derivatives. Here, delta is the spatial Laplacian. And this is to be contrasted with a standard relativistic theory, where, of course, the full space-time Lagrangian is of 2nd order in space-time derivatives. This theory here automatically has dynamical exponent equal to 1. It is the Euclidean field theory of the scalar field phi. The important thing is that once you move from this theory to this more complicated theory with higher derivative spatial terms, you have changed the scaling dimensions of fields. And that, of course, is a trivial observation, but it has profound consequences. So, for example, we know that the scalar field in the relativistic field theory is dimensionless in the space-time dimension little d equal to 2. Here is the dimension in any dimension. And that has really deep consequences. This simple fact that the scalar field is dimensionless in 2 space-time dimensions essentially explains the depth and power of string theory. It tells you that string worldsheets on which scalars represent the embedding of the string into the target space, worldsheets, because they're 2-dimensional, will have special properties. The theory of sigma models on a 2-dimensional worldsheet will be much richer than a similar theory in any other dimension. and including the fact that it can be used to derive Einstein's equations in the target space. So similarly, if we now allow ourselves to switch to z equal to 2, and now the power counting is different because these two terms are supposed to contribute the same scaling. So the scaling dimension of the field phi will end up being 0 in 2 plus 1 spacetime dimensions, in 2 plus 1 non-relativistic spacetime dimensions. So all of a sudden you have a prediction. And hopefully there are some of you on the mathematical side who might actually be interested in pursuing this direction. If you formulate non-relativistic sigma models with z equal to 2 in 2 plus 1 dimensions, they should lead similarly to a rich structure analogous to the nonlinear sigma models on a two-dimensional string worldsheet. So non-relativistic membranes are a beautiful generalization. You can ask about beta functions and conformal field theory properties and so on. This should lead to a generalization of things like dualities in sigma models. And we know how rich that subject has been on the mathematical side when you use only relativistic strings. Now it's possible to use these non-relativistic membranes and see how the structure is refined compared to the relativistic string theory case. But that would be a tangent. It has nothing to do with the subject of today's seminar. So let me go back to...
Excuse me, may I ask a question?
Sure.
There's it's a naive physics question. Go back on the previous slide. So the
slide?
Yeah, so the non-relativistic Lagrangian that you are discussing, you can formally view it as a relativistic Lagrangian using Stackelberg's trick, right? So can you learn something?
I wouldn't know how to do it for the scalar.
You think it's not going to work here? But okay, but maybe it's for some other.
Yeah, I'm not a big fan of using the Stackelberg formalism for gravity to turn it artificially into a relativistic theory, because I think that is precisely, it's literally rubbing me the wrong way in the following sense.
I understand. It's not what you want. I'm just asking if you sort of redo it in this relativistic.
I wouldn't know how to do it for just the rigid scalar field on a fixed Aristotelian geometry. It feels to me that here the geometry of the underlying Aristotelian spacetime, which only has no boost symmetries, it only has spatial rotations and spacetime translations. That would be very difficult to reconcile with relativistic symmetries. And in fact, there are some known physical effects. For example, an individual particle moving with a large enough momentum will self-decay into a cloud of particles with lower momenta, and that process has no analog in a relativistic setting. So I would be very doubtful that you can rewrite this theory artificially as if it were just a funny relativistic field theory.
See, or maybe something very non-local, which will not make much sense.
Yeah, or it would have some really crazy backgrounds on which everything depends, and I wouldn't know how to do it. But also, I'm not very motivated to do it because I think abandoning Lorentz invariance, it might be actually a feature of these formalisms rather than a bug. For example, in the context of quantum gravity, you beautifully eliminate many of the problematic aspects of the so-called problem of time, which is a famous long-standing problem in quantum gravity. And not having that problem from the beginning is actually a bonus in my view. So I wouldn't want to rewrite the theory artificially as if it were always relativistic, even if I could somehow integrate in enough gauge symmetries and so on to do it, because I think it would obscure the usefulness of the theory. It might actually be on the right track to solving some of the puzzles that relativistic theories cannot solve. Okay, so let's see if we can do it with gravity so that you guys have some background on this particular moving building block of the three different things being put together. So now just physically propagating gravity, I'm not making it topological yet. So this would be constructed to be an alternative to general relativity, which has propagating gravitons. It just happens that the gravitons will not have relativistic dispersion relations. So the idea is you start perhaps in the simplest incarnation by postulating that your spacetime underlying manifold, before you put any geometry on it, has the differentiable structure of a manifold with a foliation. And let's put a foliation by leaves of constant time. So far I have no geometry on it besides the differentiable structure and the foliation structure. And I can put a metric on this. and I'll write it in useful variables instead of writing it as if it were a standard relativistic metric with indices mu and nu. I'll take the spatial metric and I'll add the so-called lapse and shift variables. Those are known from the Hamiltonian rewriting of general relativity, but they are very useful as kind of first principle fields in the geometry of essentially pseudo-Riemannian geometry of these foliations. So if you want to know the more precise origin of these variables, the lapse and shift are basically the time and time-space components of a vielbein of the full d+1 dimensional metric. And then Gij is obviously just the spatial part of the full metric. Okay, so these will be our fields. They look the same as in GR. They are just labeled by these Hamiltonian labels. So I haven't changed really the set of fields. I've changed the symmetries because now we can only postulate as our gauge symmetry foliation preserving diffeomorphisms. So let's call them by this name. And then we can ask, what is the simplest action I can write? I'm organizing the action as a quantum field theorist from the lowest dimension objects to the higher dimension. And I'm hoping that there will be only a handful of lowest dimension terms, which will be self-contained under renormalization, depending on which dimension I'm in. So let's start with the kinetic term. The kinetic term will have to contain 2 powers of the first derivative of the metric. I'm assuming time reversal symmetry here. So I'm not interested in building some exotic theories which would have only the first time derivative in the kinetic term. So there will be a square of the extrinsic curvature of the spatial metric. So I think the notation here is self-explanatory. Nabla is just a spatial covariant derivative with respect to the spatial metric. Notice that you need the 1/n factor in order to make this covariant. And then the interesting thing is you can square this extrinsic curvature in order to build a kinetic term in 2 inequivalent ways. Either you contract the indices this way, or you take the trace first and square the trace. So the bottom line is now that there will be not just 1, but 2 possible coupling constants in this kinetic term. I've factored out one of them as an overall coupling 1/kappa squared, and I'll do the same in the case of the topological gravity system when we get to that point. But there's also another coupling little lambda. And if we were constructing general relativity, we would be adding time reparametrizations to build the full space-time diffeomorphism symmetry. And this lambda would be automatically locked to be equal to 1 by that extended gauge symmetry. But we are not interested in extending the gauge symmetry to general relativity, and therefore lambda is a parameter which is an arbitrarily real number a priori. And in principle, it should run with the renormalization group. And then besides the kinetic term, I can also ask, what else can I add to the Lagrangian that does not contain time derivatives? I'll refer to that just generally as the potential term. So it can depend on components of the spatial Riemann tensor, spatial derivatives on the Riemann tensor, various contractions of those things, but no time derivatives. And then in this term, we have many choices. We can choose to keep, let's say, only the cosmological constant term, no derivatives. That would be a silly theory, but even that has been studied in the literature in the past. We could start adding first powers of the Ricci scalar, for example, so second spatial derivatives, and we can keep going. We can organize terms that can come into this potential by the dimension. The dimension is defined by that underlying scaling that we are interested in. So you see that you have a much broader spectrum of possibilities. Depending on which dimension you are in, you might choose to construct a theory which is power counting renormalizable by allowing terms that are of a certain dimension up to the marginal dimension operators. And there will be a finite number of such operators, typically in any sensible dimension. And then you can, in principle, start analyzing by Feynman diagrams the renormalization group properties and see if the theory is indeed UV complete and whether it has some interesting physical properties. There is finally one last technicality I wanted to mention. Since the group of spacetime foliation preserving diffeomorphisms is locally generated by space-time dependent diffeomorphisms and only time-dependent time reparametrizations, it is consistent, if you choose to do so, to restrict the lapse function. The lapse function here plays the role essentially of the gauge field associated with the time reparametrization. So you don't have to allow the lapse function to be a space-time field. You can make it projectable and allow it only to be a function of time. That version of the theory is known as projectable theory of gravity with anisotropic scaling. But if you choose not to do so, you allow n to be a full space-time field, then you'll find new ingredients that can now enter into the construction of Lagrangians. In particular, you can take the gradient of n properly normalized, or gradient of log n is a nicer object slightly. And this will transform as a standard vector field. You can use that vector field to build new invariants. So the Lagrangian will be even richer. And you might be interested in classifying some of the lowest dimensional operators to see how many independent couplings you get. So the parameter lambda, again, this lambda from the previous transparency is so important. I want to remind you where it came from. It's this relative coupling constant between the two kinetic terms, which will be equal to 1 in GR. If you expand this theory around Minkowski space, it happens that the theory is perturbatively unitary for lambda either greater than or equal to 1 or smaller than or equal to 1 over d. I'm showing this transparency mostly to give you a heads up that when we talk about the topological quantum gravity construction in a few minutes, we'll see an important role being played by this parameter lambda. And again, at the risk of spoiling the punchline, we'll see that we'll be naturally driven to take lambda to either plus or minus infinity. And that will be precisely where we make exact contact with Perelman's equations. So I'm going to skip some of these other transparencies about the renormalization group properties of the non-relativistic quantum gravity, and let's finally construct our topological version of this quantum gravity. So now my intention is to do the following. In the original days, at the end of the 80s, beginning of the 90s, when topological quantum field theories of the cohomological type were first constructed by Witten and followers, it was quickly realized that this essentially represents an algorithm or a cookbook recipe, where if you give me a list of interesting fields on some manifold, give me some symmetries that you require, and maybe pick some equations that you want to play a prominent role, then you can engineer a construction of a topological quantum field theory that localizes the path integral to the solutions of that set of equations. So that's roughly the algorithm that we decided to follow and combine the fields of non-relativistic Lifshitz gravity with the equations of Perelman's Ritchie flow. So for me now, the starting point, now I'm really constructing the topological quantum gravity theory. So I'll start on a manifold, which is a foliation. Let me, for simplicity, imagine that the foliation is global. Sigma d is a compact spatial slice. The extension to non-compact spatial slices should be possible. Presumably, you need the condition of complete manifolds, complete Riemannian manifolds, but the boundary conditions near infinity have not been studied carefully, so I'll be restricting myself to simply just compact spatial slices. And for now, let's just consider the structure without some fancy effects of Ritchie flows with surgery. So I'll assume that I'm on a patch of the manifold, which takes topologically the form of a compact interval between some initial and final time for which I'm following the system cross sigma d. This does not mean yet anything about the geometry. This is just a topological assumption. And following in Witten's footsteps in how the cookbook works, I take my field Gij, the spatial field. This will be the simplest possible, the most primitive theory. I know that Perelman's equations, or better yet, going all the way back to Hamilton, Hamilton's equations contain a spatial metric, so let me not postulate yet any other field. And let me say that the theory will be topological. There was going to be a topological BRST charge Q, so that's a cohomology charge. It squares to 0 on the space of fields. And it's this cohomology of the BRST charge that controls all the physical properties of the path integral, as usual, for example, in the more elementary case of topological Yang-Mills gauge theories. So the story is supposed to be quite similar to that, even though there are some later subtleties that might kick in when we talk about moduli spaces of solutions and such. But at the level of constructing the physical theory, I'm postulating a Q, the anti-commuting BRST charge, maps Gij to some Grassmannian field psi ij, and this will be the ghost of topological symmetry. So I'm postulating that there is an underlying gauge symmetry that deforms the spatial metric Gij by an arbitrary two tensor locally. And in the BRST gauge fixing of the gauge symmetry, this translates into the existence of this fermionic ghost psi. And now in order to construct a meaningful Lagrangian, first of all, what is the Lagrangian that will be invariant under the naive topological symmetry that Gij is being deformed arbitrarily? Up to topological invariance, as usual, the Lagrangian is just zero. So we need to construct a Lagrangian which is non-zero. It gives us propagators for all the involved fields. In order to get those, we need to introduce a new multiplet, an anti-ghost auxiliary field multiplet. So chi-ij will be also a Grassmannian field. It happens to carry the same tensor structure as the ghost. That's an interesting coincidence of the Ritchie flow. My intention is to construct a theory such that the path integral localizes to the Ritchie flow equations. And Ritchie flow equations happen to have the same tensor structure on space as the metric itself. The fundamental variable has the same, is a section of the same bundle as the right-hand side of the Ritchie flow equation, if you think about it from the point of view of the spatial slices. So because the auxiliary field Bij is going to be the one imposing the localization condition, and because I want the localization to be the Hamilton-Ritchie flow equation, I have to postulate that Bij and chi-ij are, again, modulo statistics, the sections of the same bundle. So now that we have these basic fields, we can start writing down Lagrangians in components, but we can also do something quicker as a shortcut, as a very useful tool to generate results more quickly and in a more compact way. We can introduce a nice superfield by introducing two Grassmannian real variables, theta and theta bar. The bar here is just an index. It does not represent a complex conjugation. That's a physics type of notation. So now I have, instead of a field on time and space, I have a field which is extended to a superspace which has two additional real Grassmannian dimensions. And when I expand a metric, a spatial metric on this superspace into components, I get these four fields, the ghost, the anti-ghost, and the auxiliary, together with the metric inside one superfield. So using this capital G superfield, we can now start writing down interesting theories. Why is this n equals 2 superspace useful? Well, because it kind of jumps out at you when you are observing the structure of the multiplets of the BRST symmetry that are consistent with the Hamilton-Ritchie flow, but also because they reveal the possibility of imposing a larger symmetry. So instead of saying that the theory is invariant only under the BRST charge Q, we can just decide that we require more symmetry. Instead of Q, there will be also another BRST-like charge, Q bar. This is just a spectator. It is not something that would somehow enter into the definition of the BRST cohomology of the physical states. But it will be useful to require this extended supersymmetry. We will require that Q and Q bar anti-commute to time translations, simply because that's the only way in which you can construct a theory which localizes to Perelman's Ritchie flow, or in this case, Hamilton's Ritchie flow, consistently with the renormalization group. So we don't want to open up the room for many more terms that would spoil this connection to Hamilton and Perelman. And typically, that requires a certain degree of supersymmetry. Here we need Q and Q bar, and we need them to anti-commute to the time translation generator in order to generate the correct flow equations from the variational principle. So now we can postulate the simplest possible action. By the way, these D bars are the natural superderivatives on this superspace. maybe I should clarify that unlike in relativistic field theories, what we are supersymmetrizing here is not space-time, it's only time. Just the one time dimension is supersymmetrized. The spatial bosonic slice, sigma, is just a spectator. It does not get any fancy supersymmetrization. So we have a 1/2-dimensional supertime and a spatial d-dimensional bosonic geometry. So on this superspace, we can write down the generalization of the Lifshitz type action. Again, the story will be very similar. You'll have two time derivatives hiding inside here in the superderivatives. You'll have this relative coefficient little lambda, which can appear for the same exact reasons as in the bosonic theory. And you can also start organizing the spatial derivative part of the potential usefully by saying it starts off with the cosmological constant term. Then the next term would be the Ricci scalar superfield made out of the space-time supermetric on space, and so on. You can have higher and higher derivatives. The good news is, perhaps, at least from the point of view of the Ritchie flow, the entire Ritchie flow structure will be captured by stopping at order 2 in spatial derivatives. The next term here of higher order in spatial derivatives would perhaps be of order 4 in spatial derivatives. That will give us in components flow equations which have many more derivatives than we need, and that keeps the theory simple in this language. So we'll only need a handful of these coupling constants, alpha lambda, alpha r, and I'll introduce one more, perhaps in 5 minutes. In our next iteration of the story, you'll see how closely we will then get to this so-called superpotential term in this theory to be mimicking the structure of Perelman's F functional. So again, as another spoiler, the F functional of Perelman's will essentially appear as the superpotential in our theory. That's yet another, in retrospect, that's yet another reason why we required the extended n=2 supersymmetry, so that we have this nice crisp notion of a superpotential, and we get the right-hand side of the flow equations from the variational principle. So we can construct the theory, plug everything in, look at components, and you find out that, again, I'm skipping the technicalities, but they're really elementary and go back to all the way to the original topological Yang-Mills constructions and such from the late 80s by Witten. The logic is exactly identical. You localize to the solutions of the Bij=0 equations, and they happen to be of this form, where lambda tilde is related by this, well, lambda tilde is something like 1/1 minus lambda times d. So it's a function of lambda. But it doesn't matter the technical details. The important thing is that if you stare at these equations, first of all, it's easy to evaluate the variation of this W functional. And you find out that for the values of the couplings where alpha r is 2, the cosmological constant has been set equal to 0, and lambda tilde takes this arbitrary looking value. Whenever you dial these three values of the couplings, the right-hand side is exactly Hamilton's Ritchie flow. So you get the localization equation to follow as the exact localization equation from this action to be the precise Hamilton Ritchie flow equation. So it's still true that the full variational principle equations of motion will never give you Hamilton's Ritchie flow equation, no matter how hard you try. That's easy to prove. But you can get them as the complete localization equation in this most primitive version of this topological quantum gravity. So now let's make the theory fancier. That was my punchline number 1. We can get Ritchie flow of Hamiltons out of localization. And now I will try to fancify the theory as any physicist would by adding gauge symmetries. So the first thing I'll do, I'll start adding those gauge symmetries from the Lifshitz gravity setting. I'll try to make the theory invariant under space-time dependent spatial diffeomorphisms. In order to do that in the bosonic setting, you are supposed to introduce that shift vector, which I called capital Ni before. Let me call it little ni now, because I'm reserving capital Ni for its associated superfield. So I'll introduce the shift vector Ni and its superpartners, because I'll be building the theory consistently with the requirement of n=2 supersymmetry of supertime. So long story short, you have to covariantize all the derivatives. This is a really enjoyable detour into super connections and super geometry, but relatively algorithmic. You find constraints so that you don't end up with too many component fields and so on. And when the dust settles, you find, and of course, there's also some tangential geometric interpretation, which I don't think we have time to get into, but they're tangential to the punchline. And finally, you can write down actions for this theory. Now that you've sorted out all the component fields and wrote down everything in terms of superfields, everything nicely simplifies again, with the only novelty being that these derivatives, the superderivatives on the metric in the kinetic term, are now these fancified covariant superderivatives that I quickly introduced here. So never mind the details, this is all in the papers and can be easily understood geometrically. There are now just covariantized derivatives that make everything consistent with space-time dependent spatial diffeomorphism gauge symmetry.
Petr,
yes.
So you made a special choice of parameters to match Perelman results. Do you see why is that the right choice? Are the others not interesting for some reason? What's special about those?
And you are ahead of me by about 5 minutes, I think, because I haven't even gotten to Perelman per se. The only thing I was able to do so far was Hamilton's flow. Now I'm on my way towards Perelman's flow, but that question is the perfect question to ask because, of course, all these couplings in this quantum field theory, in principle, they run. And the question is, why do you dial some specific values for them? You'll see that there is a very good reason. There is an enhanced symmetry that plays a role when you try to dial lambda equal to plus or minus infinity. So that value can be protected by symmetry. And that will indeed be crucial because that's going to be, again, to get ahead of my punchlines, that will be the way in which we impose dynamically the Perelman volume condition. It will automatically come as a consequence of the fact that the theory at lambda equal to infinity or minus infinity is actually spatially unimodular, essentially. And as far as the values of the other couplings, once you get to the point where you are precisely trying to reproduce the Perelman flow at all scales, I think what you have to perform is what I would call topological renormalization. You zoom in as you follow the renormalization group flow. Perhaps some of these couplings, maybe alpha r, might change by a little bit as you change the scale infinitesimally. But then you don't have to restart the RG flow and go further. You can, at that point, take a break, rescale the couplings slightly back to their original values. And you can do that by deforming the theory by a Q-exact object. So you are not changing any correlation functions. You can still retuning the couplings to be always of the same value at all scales. And you can try to push this all the way to the UV. So I would call that topological renormalization. A Wilsonian renormalization, which is by small steps, very similar to what the mathematicians would call the Gromov-Hausdorff limit. As you're zooming in on the geometry in small increments, you're doing it in a controllable fashion, but in this physical setting, you would also be required at each intermediate step to rescale the couplings back to the original value. And you know that the change is Q-exact. So that's my quick answer. And if this requires a longer answer, then maybe we can talk about this at the end or after. Is that okay? You know?
Yeah, go ahead. Great.
Okay, great.
Excellent.
Thanks. But it's an excellent question, and actually we did spend some time working on it, but have not yet published a final word on that subject. So what's the bonus of having space-time diffeomorphisms? Spatial diffeomorphisms which depend on space-time. Long story short, we can now perform the Deturg trick, which is simply just several different gauge choices that are available to you for the spatial diffeomorphisms as space-time gauge symmetry will give you different implementations of the Deturg trick. So that's the punchline here. And then since I'm almost out of my original time, did we start 2:15 or something? Sorry, 1:15? How much?
As you know, in the seminar, we're flexible with time, so you really should not, there's no
I know, and
nominally we usually go for 2 hours. So
I do appreciate this, but then you're running the risk. I may have many more transparencies, so we might be here for hours. So I think we will have to strike some kind of compromise. I don't want to exhaust the audience completely.
I think our priority is that the speakers get a chance to explain their story well. So, and we get to ask the questions. So
in that case, I should have been talking more about these previous transparencies. There's only one, retroactively, one comment that I skipped over just now, which I think is worth pointing out. I'm not sure what it means exactly. All the consequences are not yet clear, but it's actually quite surprising when you formulate this gauging of spatial diffeomorphisms procedure that I just outlined here, these covariant derivatives, ... You go through all that process, understand it geometrically, and then you stare at the result. It actually takes a surprisingly familiar form of just standardly constructing a super Yang-Mills gauge theory, supersymmetric Yang-Mills in superspace, while choosing the gauge symmetry instead of being some SUN or some other internal gauge symmetry to be spatial diffeomorphisms of sigma. So you fix sigma and you formally define this infinite dimensional, at least Lie algebra of diffeomorphisms of sigma. And when you perform this conventional standard construction of super Yang-Mills in superspace, including introducing super connections associated with this, you then, in retrospect, get on the nose the construction that we found. And I find this surprising. I don't see there was any reason why the conventional super Yang-Mills construction should be extendable so directly to the case of spatial diffeomorphisms as a gauge symmetry. It would not work with all space-time diffeomorphisms. And it reminds me of the puzzle that Zvi Bern and his collaborators are encountering in the so-called BCJ duality. They've been looking for a good explanation why when you replace, so there's this magical relation between amplitudes in Yang-Mills gauge theory versus gravity theory, supersymmetric or non-supersymmetric. And the idea is, roughly speaking, Yang-Mills gauge theory amplitudes take the form of a product of an internal color factor times a space-time kinematic factor. On the other side, gravity has no internal color factor. It has only 2 copies of the space-time kinematic factor. But when you perform the replacement, they map onto each other, and this seems deep and important. Now the question is the kinematic factor on the gravity side in particular somehow intrinsically also related to some internal Lie algebra symmetry? Since you're replacing the original Lie algebra Yang-Mills structure with something kinematic, what is the geometric Lie algebraic type of explanation that this works? And to my knowledge, they have not been able to find any direct mapping. This is the closest I've seen as far as a standard Yang-Mills structure jumping out of a gravity setting. And it's at the cost of sacrificing Lorentz invariance. Only when you focus only on the bosonic spatial diffeomorphisms, you get this strange identity that this construction is precisely just on the nose super Yang-Mills in superspace. So that's my comment I wanted to return to because.
But a super Yang-Mills with broken Lorentz invariance again, right?
Well, there was no Lorentz invariance here to begin with, so it wasn't broken. But the question is, what would happen if you tried to redo this in the original BCJ framework, starting with the relativistic theory, sacrificing Lorentz invariance temporarily, getting this group structure, and then can you somehow make it again consistent at the end with Lorentz symmetry? Presumably, if the construction is complete, then it has to be secretly Lorentz invariant. So maybe you need some temporary abandonment of Lorentz symmetry to make this Lie algebra structure more explicit. But again, I don't really have any progress or any comment on that. I just thought that this might be an interesting point of contact with that long-standing puzzle for the BCJ duality.
Therefore, for the BCJ, I thought there was a derivation by Bo Feng et al. From, in the Yang-Mills case at least, from
well,
rewriting it in terms of the structure constants.
It's not a complete derivation by any stretch, as far as I know. Maybe I've not seen what the latest word is on that, but I thought that that was found perhaps inspiring, but far from providing any complete explanation. It's more of a hint of some structure, some kind of area preserving, volume preserving diffeomorphism or something. But I'm not sure what the current status of that is. So maybe they've already made more progress than I'm aware of. My cat is complaining about it again. My cat might know about BCJ more than I do, but I'll ask him after the talk. Let's see. So back to the main point, and we're almost there, so I'm not going to be too abusive of the generosity in time. I'll try to add one more symmetry. Of course, we know from the context of Lifshitz gravity that it should be some form of time reparametrizations. On the other hand, why would you want time reparametrizations? From the point of view of Perelman, those equations have never been time reparametrization invariant, even in the projectable sense. So we know that in the end, we'll not be successful if we insist on unfixed time reparametrizations as being the full symmetries of the theory. You can also, of course, entertain the possibility of treating these space-time symmetries equivariantly. This would be very similar to what happens in Yang-Mills, where you treat the topological symmetry as the primary topological symmetry, and then the secondary Yang-Mills gauge symmetry, which is still there, you treat equivariantly, and you define the equivariant BRST cohomology. Turns out that even that trajectory, even perhaps it might make sense as a construction, it would still take us, as far as we can see, away from Perelman. So we'll have to make choices, and there are different motivations. Somebody might be interested in an equivariant BRST cohomology with respect to, let's say, space-time foliation preserving diffeomorphisms, but that will not give you on-the-nose Perelman. So I'll be mostly focusing on what do you get when you try to match Perelman. So in the intermediate stage, I will try to look at those time reparametrizations and extend the gauge symmetry. So again, we need to introduce the appropriate gauge field. In this case, it's the lapse function n. I'll again call it little n. When I was reviewing Lifshitz gravity, I called it capital N, which is its usual notation in the literature. But here we'll treat little n as the bosonic leading component in a superfield, because we are formulating everything in superfields since it's so much more efficient than doing things in components here. So for example,
sorry, the fact that you don't have time translations, that's natural, but you should have time reparametrization symmetry, right? That you have. Well, like in a theory with gravity.
Not as a gauge symmetry. The equations are not invariant under time reparametrizations. They're covariant.
Isn't that strange in a theory with gravity? So you somehow really don't have then.
You only have time.
You don't have a d plus one dimensional gravity. You have only d dimensional gravity. Well, is that how I should understand for this?
I would like to show you how you do have d plus one gravity, and that will be basically the punchline of maybe the next transparency. So I would claim that Perelman, he was not interested, probably. I don't know. I cannot know what was in his mind when he was doing this construction, but I'm guessing he was not interested in constructing a d plus one dimensional gravity theory. We were interested in d plus one dimensional quantum gravity, and we found a reinterpretation of the story, which I'll show you now, leads to a d plus one dimensional quantum gravity. So let's try to promote time translations into a gauge symmetry of time reparametrizations and make the theory consistent with that gauge symmetry. So we are again introducing that lapse function, and I'll make the lapse function a space-time field. In other words, I'll use the so-called non-projectable version of Lifshitz gravity. That is the more general setting and also popular for phenomenological applications of quantum gravity, or for holography. You need to go to the non-projectable version where n is a space-time field. And once you, again, there are some connection superfields that you need to introduce in order to covariantize derivatives. I'll spare you the technical details. Just the explanation of the notations and the constraints would take another hour at least. So this is in the papers. I'm happy to chat about it after the talk or by email if anybody wants to see the brute details of the construction. But roughly speaking, you take the original derivatives that you started with, for example, the spatial, the time derivative of the spatial superfield metric, and you have to covariantize it simply by multiplying it by a superfield, which is essentially a component of the field bind, geometrically speaking, in superspace. So when this all is dusted. The non-projectable theory involves some awful looking constraints, but those are very unique and easy to justify geometrically. And finally, we are ready to write down the action for this non-projectable theory, which we are still expecting to have, just to summarize, space-time dependent spatial diffeomorphism symmetry, and now the newly introduced time reparametrization symmetry in a way consistent with superspace. So this has been done in our papers. This was actually already in paper 1. And the action will again have two terms. There's going to be some overall coupling 1 over kappa squared, which I'm factoring out. This is, by the way, the one which you want to use in the BRST argument to prove that the partition function localizes to the semi-classical solutions of the localization equations. It's the fact that the changes in kappa squared are Q exact, because the entire action is Q exact, that controls that standard semi-classical argument. So kappa squared is just essentially h bar factored out of the whole thing. And then I'm left with this little lambda parameter will play an important role, but let's keep it generic for now. And I'm organizing my action here from the lowest dimension terms, the cosmological constant here, alpha lambda, that's just a number. We decided to call all the couplings in this superpotential alphas so that we all keep track of where they come from. We have the alpha r, the coefficient of the spatial Einstein-Hilbert term in the action, but we have a novelty. Remember when I talked about non-projectable Lifshitz gravity, there is a possibility of having a gradient of n. Let's call log n, actually minus log n capital phi, so that we can eventually match Perelman's notation. And observe that this superpotential that we now have, based on the arguments from Lifshitz gravity, allows at the same dimension as the Einstein-Hilbert term enters, we also have a second power of the gradient of the field phi, log of the Labs function. Also, you notice when you stare at this superpotential that it has formally a very similar form as Perelman's W or F functional, the original F functional. If you make the proposal that our superfield phi, in other words, the log of the Labs function of the D plus one dimensional geometry, be identified with Perelman's dilaton field. Similarly, here we have a factor of n. So if n is e to the minus phi, oops, I didn't mean to click on it. If n is e to the minus phi, this is going to be the famous e to the minus phi prefactor sitting outside of the integrand in the Perelman F functional. So that's our proposal here, and it's somewhat surprising perhaps, and it's an interesting twist. We were surprised and pleased that in order to make contact with Perelman, we do not have to introduce some arbitrarily randomly chosen extra scalar field phi. Instead, we have automatically in the four-dimensional or D plus one dimensional space-time geometry, we have the Labs function, and the log of the Labs function plays the role of Perelman's dilaton modulo how you choose these couplings. For us, these couplings are unconstrained. They would lead to whatever localization equations they lead to. They'll generalize Perelman's equations. But formally, this is the construction that at least establishes the connection between Perelman's quote-unquote dilaton. We don't interpret it as a dilaton in our D plus one dimensions. We interpret it as the log of the Labs function. So this partially answers Mina's question. That this is how we see this as a D plus one dimensional geometry. We find this perhaps surprising twist in interpreting the original field phi as actually having to do with the Labs rather than some kind of a dilaton of string theory. So we can now derive the localization equations. There will be an ugly mess because they depend on many couplings. This is just happens to be presumably the correct form that I quoted from our paper. And you see here in white, those are the terms that you want. And here in yellow is some other extra stuff that we would like to eliminate by a judicious choice of the couplings. So in order to see, again, this is the subject of our third paper. So the detailed arguments, it's not a short paper. So the arguments go through several steps, but I'll spare you the intermediate steps and show you that you need to do two things. in order to establish a contact between these localization equations and Perelman's equations, you have to identify phi, r log of the lapse function with Perelman's dilaton. You have to notice this unpleasant extra factor of e to the phi that we automatically got in our variables. This type of factor is not there in Perelman's flow equations. The left-hand side had this replaced by just 1 times the time derivative of the metric. So we have to figure out how to get rid of this relative e to the phi. And the way to do it is to, of course, invoke the fact that whenever you have a spatial geometry described by some metric, and you have something that transforms from the point of view of the space as a scalar field, you can perform frame redefinitions. You can rescale the metric by some function that depends on the dilaton. This is common in string theory. We rescale between the string frame and the Einstein frame and various D-brane frames all the time. Typically there is no unique geometry which is better or more superior to the others, depending on which observer, which kind of brane or string is observing the geometry. They see naturally a different reframing. So we should allow ourselves this reframing. After all, it's just a change of variables on the space of fields. So nobody stops you. And it turns out when you perform this change of frame, you define, and now I'm confusing myself, which variables are ours and which are Perelman's. I think in the paper, we decided to call Perelman's variables G hat. Here I'm calling them G tilde because I'm using slightly old-fashioned transparency in this particular place. Perelman's dilaton is phi tilde, and it's related to R variables phi and G through this transformation. So long story short, you perform this transformation of variables, and then you still have to be somehow facing up to this missing condition of why the volume element should be fixed. Perelman chose this strange combination, strange to us. It was probably completely obvious why to choose that combination to him, but to me, there is a square root of Perelman's metric. There's e to the minus the Perelman dilaton. What does this mean in our variables? We determine our variables. This switch here was completely determined by trying to map the shape of the equations. So there was no freedom in it. And once we perform this reframing to our variables, it's a beautiful fact that Perelman's fixed volume condition in our variables becomes simply the time independence of our volume element of the metric in our variables. So there is no leftover factor of a dilaton, and shows you also a very elegant way how to obtain this equation automatically dynamically. I knew, based on my experience with Lifshitz gravity, with propagating gravitons, that this type of unimodularity of the spatial metric happens dynamically precisely in the limit where the lambda parameter of the kinetic term goes to plus or minus infinity. Actually, I think we like minus infinity in this context slightly better than plus infinity, simply because if you choose minus infinity, that will make the entire action manifestly bounded from below, and the path integral is even in a better shape than in some of the sketchy cases of quantum gravity where you have unbounded Euclidean signature actions. If you choose plus infinity, this might be more intuitive from the point of view of GR. After all, you are deforming on the same sign of the values of lambda, but that would leave you with the same problem of the conformal factor of the spatial metric having the wrong sign in the Euclidean action, and you would have to somehow analytically continue to make sense of the path integral. So I would suggest that minus infinity is the sweet spot value of lambda. And once you choose this little lambda to be minus infinity, then the localization equation becomes, in this case, a beautiful superposition of two equations, each of which separately is the two equations of Perelman. The reason why they appear as a linear superposition is, remember, here I was still insisting on time reparametrization symmetry, which is not there in Perelman's equations. Turns out this way of obtaining essentially one fewer localization equation is the only linear combination of Perelman's equations that you can take in order to make the result consistent with unfixed time reparametrization invariance. So to summarize the punchline of this part of the talk, once you understand how to incorporate the lapse function, you can make the theory gauge invariant under time-dependent time reparametrizations. You can get very close to Perelman. The localization equation will be a specific superposition, missing one equation which would break time reparametrizations. And the remaining question is, how do you construct a theory which just matches Perelman? So obviously, this is not going to be a very complicated process from now on. Now you can just take the same setting, the lapse function, the shift vector, and the spatial metric will be the variables. You supersymmetrize as we have done so far, and choose a slightly different gauge fixing fermion in order to construct the BRST action, which does not have any residual time reparametrization invariance. After all, that's what Perelman's equations are asking you to do, to gauge fix whatever gauge symmetry acting on time you have to gauge fix it in order to match Perelman's equations. So that final step, I don't even have a transparency on it, but that gives you on the nose the localization equation. When lambda is equal to -infinity, the path integral has a Euclidean signature bounded from below. And by the physics standard of rigor, you have established localization to the solution of the Perelman equations.
Again, what is a theory where coupling is simply infinite mean? Does it mean that whatever the coupling stands in front of should vanish?
Well, you can treat it in
different... Or it's a constraint, right?
No. It's, well, if you happen to find yourself in that set of values of the couplings where lambda is close to infinity, it turns out that there is an additional symmetry when lambda is exactly plus or minus infinity. And this type of quantum gravity theory is not subject to some of the bounds on non-existence of global symmetries from relativistic systems. So relativistic quantum gravity, sometimes you hear people saying there cannot be any global symmetry in quantum gravity because of black holes, roughly speaking. Here, there is no obligation against global symmetries, and you can use this global symmetry to protect the value lambda equal to plus minus infinity. The question is, how do you implement it in the path integral? What does it mean in the path integral? If you use the original naive unrescaled variables, then if you take lambda to minus infinity, it simply suppresses infinitely all the contributions from the field configurations which would not satisfy this condition. So in that sense, it appears automatically as a constraint that is respected by all the field configurations that contribute to the path integral. Or you can see it even more in a more elementary physical way by finding the right variables. In the lambda goes to plus or minus infinity, the naive fields that we started with are not the best variables. You perform a nicer change of coordinates to nicer fields, and then you can take this limit, lambda going to plus or minus infinity, as a smooth limit in the Lagrangian, and you see the same consequence, that you're basically localizing to unimodular spatial metrics. So both of these procedures, I think, are really under control from the physics point of view. It's not some strange singular limit where things will be blowing up in the Lagrangian. Does that answer the question?
Yes.
Okay.
And sorry, just one more thing. Yeah. What we gain by this is reparameterization symmetry in time. So that's why this was a good thing to do.
It was there, but now in retrospect, again, this was one of our state-of-the-art summaries at some point during the project, but then we were frustrated that this takes us away from Perelman. So why should we be even interested in this more equivariant type of theory where we still have some foliation-preserving diffeomorphisms as a gauge symmetry? Shouldn't we just design a theory which in one swoop gauge fixes the entire lapse, shift, and metric variables such that we localize precisely to Perelman and have no residual time reparametrization? And that to me is the quickest, most direct way towards Perelman. And it completely eliminates this necessity of discussing time reparametrizations as long as you have the full ADM decomposition variables of the full space-time metric. So you have the lapse, the shift, and the spatial metric. You end up gauge fixing and not having any residual time reparametrization simply because that's the symmetries of Perelman. So in Perelman's theory, he discusses also two more functionals, at least in the original paper or papers. There's the F functional, which I've already explained quite explicitly as being our superpotential. He also has, so just as a quick background, the F functional of Perelman is a good functional if you are mostly interested perhaps in static configurations. If you are interested in configurations that are shrinking or expanding with time in the context of Perelman's Ritchie flow, then you might be better served by switching to his so-called W functional, or the generalization that was later on postulated by Feldman, Ilmanen, and Nee, called the W plus functional. So those are somehow the best functionals that represent how much we can control the notion of entropy, roughly speaking, for expanding or shrinking solitons, or in the reverse order. W is designed to capture the shrinking soliton behavior. W plus has some sign changes and corresponds to the expanding solitons. So what is this W functional? This looks very mysterious because in addition to the original fields, Perelman all of a sudden introduces this function tau, which is only a projectable function of time. It's not a space-time field. It only depends on time. And the desired localization equation should be the time, this function tau, the first time derivative of tau should be -1. So essentially that's a fancy way of saying that tau is just a linear function of time. What kind of a place would we possibly have for such a strange field in the context of superpotentials in topological field theory? Well, we found a very simple answer to that question in our third paper. Towards the end of the third paper, you can look it up and you find the following construction. I don't have a good transparency explaining the details of it, but I just want to explain in words. It will not take long. So you take the original system as I've constructed it for you before, and you couple a trivial system where you postulate one new superfield, call it capital tau, and this capital tau by design will be only a projectable field of time. The kinetic term for this new tau superfield will be simply the superderivative of tau times superderivative bar of tau. So the equation of motion is free. This is a completely free superfield coupled to the rest of the system. And now, if you perform a judicious change of variables that mixes the variables of the metric sector with this new free field, so this is just the transformation at the level of the bosonic components, it involves some mixing in of this tau. Quite magically, the localization equations of our combined system, when expressed in terms of these variables, give you precisely this generalized W functional flow of Perelman. And the same story is true for the parallel case of W plus. So what is the interpretation of this field capital tau? It is essentially a Stuckelberg field, or a Goldstone field in a sense, for spontaneously broken time translations. It looks like what's happening if you go to the case where the dominant configuration of the flow is a shrinking soliton, then of course, compared to a static solution in time, this is spontaneously breaking time translational symmetry. And in physics, we know very well how spontaneously broken time translations require Goldstone modes. If you put in by hand this Goldstone mode and change the variables accordingly, you can now find this extended formalism where the Ritchie flow equations contain this flow on the Goldstone field tau, and give you exactly what Perelman just pulled out of thin air for mathematical reasons as this combined W functional flow. So I find it, again, quite amazing as yet another indication how often these physics ideas and math ideas, without realizing that they were approaching the same structures from completely different motivations and origins, how often they mesh together and kind of support each other in this construction. So
what are the shrinking Ritchie solitons? What is this good for?
There are books on them. What you want to be doing, again, I'm no expert. There are many people in this audience who could explain this much better. But the idea is you want to start with some generic initial configuration, some very complicated metric, and you want to uniformize it somehow. So you want to be decomposing it into more controllable pieces. And so, for example, you want to be studying solutions of the Ritchie flow, which exist for a very long time, so that they can mimic the asymptotic behavior of these limiting processes as you're decomposing the complicated object into simpler pieces. And so there's a classification of objects that are either living for a long time from the past or living forever into the future. And they exhibit typically some nice scaling properties. And you want to be able to find quantities which are bound from below or above that are monotonic along these flows of these solitons. So these W and W plus functions are roughly the best guesses that allowed people finally to find enough bounds on the monotonicity of various geometric quantities so they could predict exactly what kind of possible endpoints of this evolution can the complicated initial configuration decompose into. That would be my very naive big picture summary of how I understand what these solitons do. But you can forget the solitons. You can just ask, why is this important W functional showing up? And do I have a physical explanation for it? And the answer is it's showing up whenever the background Ritchie flow breaks time translation invariance spontaneously. And the physical meaning of this tau field is actually like a projectable Goldstone field of conventional physics systems with broken symmetries. So I think I'm close to conclusions now that I'm half hour over my original official time. So I just wanted to point out one cute thing, which perhaps might be physically interesting. If you look at any solution in Perelman's frame, the original variables that Perelman postulated, it will have this typical behavior. I combine all three types of generic behavior here into one. That you can have spheres or spherical-like positively curved chunks that eventually disappear at finite time into nothing. You can have topology changes through neck pinch singularities. There are two examples of those. Or you can have chunks that expand forever because they are hyperbolic, roughly speaking. This is just an oversimplification by a lot, but it gives you a sense for what to see in Perelman's variables. If you reframe into R variables, this same configuration picks up one interesting new feature. In R frame, the metric is just happens to be normalized for reasons that have nothing to do with how the metric should evolve. It was out of the construction of the matching of the equations in the localization and such. The spheres that are in Perelman's frame shrinking in finite time, in our case, they just round themselves up and they keep going forever. They exist forever simply because you have essentially renormalized the volume to be fixed for a round sphere forever. And similarly, the hyperbolic pieces would also not expand dramatically over time. They would roughly homogenize and stay of some finite volume. That's the important thing. So it gives me some sense of how different frames have not been really used up much on the mathematical side. Maybe looking at these Ritchie flows in different frames, using the fact that the dilaton can be used to reframe might shed some interesting insights, both mathematically and physically. In physics, this would resolve the potential puzzle one might have about losing components of space-time during these topology changing processes. Can we even define what unitarity would mean in this topological field theory setting if we are completely losing some components? I don't know if there are non-trivial Hilbert spaces associated with these spheres. My suspicion is that they only contain one state, which is just the ground state. But even that is questionable once they start disappearing into nothing. Here in this frame, they actually, at least in this coordinate time, exist forever. So they don't run into issues of unitarity, at least in the preliminary analysis. But that brings me to a long list of open questions. So I'll probably just leave them on the screen. You can read through them and ask questions about specific items. There are many interesting open questions. UV completion, using the mathematical theorems to claim whether or not, so maybe one comment, one out of all comments, I'll pick this one, this line, and I'll comment on it a little bit because it's very interesting, I think. Normally in perturbative quantum field theory, you expand around a background, you use Feynman diagrams, and you try to prove that the theory is naively power counting renormalizable in perturbation theory, perhaps. If we try to do that in quantum gravity of this Lifshitz type, then naively, if you pick z equal to 2, which is the correct dynamical exponent relevant for the Ritchie flow type of behavior, then this would naively predict that the theory is power counting renormalizable only in dimension 2 plus 1. The theory can be easily written down in 2 plus 1 dimensions. And of course, it gives you what you expect, the correct proof of the standard uniformization theorem for Riemann surfaces. So it's also a rich theory, not as rich as the 3 plus 1 dimensional one. And perhaps that's also why it's so consistent with power counting renormalizability. But now in 3 plus 1 dimensions, our theory by naive perturbative dimension counting is not renormalizable. You have to somehow work harder to provide a UV completion. So this is an interesting challenge, which again touches on what Mina was asking. If my coupling constants now start moving away from being described by the Perelman values as I change the renormalization group scale, this is more significant when the theory is formally not power counting renormalizable. Then you have to invent a procedure that allows you to kind of restore the same values of the couplings. And I think based on the insights from the mathematical side, we can say that this might lead to a novel non-perturbative UV completion. Instead of perturbatively power counting renormalizable theory, you might end up something which is not power counting renormalizable, but ends up being renormalizable in the non-perturbative sense. Namely, it would give you any answer that you can possibly want to any physics question about short distance behavior. Since those short distance singularities that the Ritchie flow can undergo have been effectively fully classified in 3 plus 1 dimensions, we can say that the full classification now gives you a full list of possibilities of what can happen at short distances as you zoom in on any singular region of space. So I think I'll end on that, and thank you very much for your extreme patience. And if I can answer any questions that anybody might have. Thank you.
Thank you, Petr, for a wonderful talk.
Hi, can I ask a question?
Sure.
Do you have, so the metric is not Q exact, right? So when you say this is topological, do you have intuition about what sorts of operators are Q exact?
Which aren't Q exact or are Q exact?
Which are Q exact?
Well, I guess the interesting question is, what is the BRST cohomology, so that we have a list of observables for which we can calculate some interesting correlation functions. And I suspect, because this is such a unique theory, it has a balanced symmetry between ghosts and anti-ghosts. So there is no ghost number anomaly. Moduli spaces, unlike in Yang-Mills, will not be finite non-zero dimensional because there is no ghost number anomaly to saturate. So you won't end up predicting that there should be some intersection numbers of some cohomology classes on the list of observables. My sense is that the interesting observables for this theory have already been identified again by the mathematicians, of course, in a different language. They will not be local operators. I wouldn't be surprised if, and this is very likely true for this simplest theory. The simplest theory that I showed you does not have any secondary ghost for ghosts. There is no need for residual gauge symmetry fixing. And therefore, the typical cohomology classes that you get from powers of ghost for ghosts in, let's say, topological Yang-Mills, they're not a part of the story here. So I wouldn't be surprised if on a local patch, which is geometrically smooth, you look at a list of all operators that you can build locally, then local operators might have trivial cohomology here. The naive BRST cohomology might be empty, but the interesting observables will be non-local and there will be extended objects. And that's often the case in quantum gravity, that quantum gravity somehow wants things to be not localizable to points. So the interesting observables are often not point-like operators located somewhere, but they're often extended branes or strings. So there is a beautiful review paper by Terry Tao, I think, on the differential PDE context of Perelman's equations. And in that review paper here, he reviews a long list of interesting observables that people have tried, starting with Perelman's L length. If you put a generalized geodesic into your geometry, you can study not just the geometry itself, but also the response of a geodesic or some generalized length or generalized area, generalized volume for various, I would call them non-relativistic strings and non-relativistic branes, which should be available because mathematicians have used them as probes. You can, for example, wrap various possible singularities around by various dynamical spheres and study how they respond, roughly speaking. So these should exist as probes at the level of, there should be a possible Lagrangian, for example, for a topological string, which would be a non-relativistic string that naturally couples to the Perelman background and evolves consistently with the symmetries of this background topological gravity. Or there could be membranes of various dimensions that again probe the background geometry. So those should be possible to write down as path integral theories just on the same lines as here, essentially asking for the analog of how do you couple a string worldsheet sigma model to a target space gravity consistently with, let's say, space-time diffeomorphisms in conventional string theory. So the same questions are available here, and I think that's my hunch that the interesting observables will be in that corner. They'll have to do with branes and strings rather than point-like operators.
So, I mean, the reason you're not including the metric as a local observable is because it's not gauge invariant? Is that right?
Yeah, you can locally gauge it away by this topological symmetry. So that doesn't mean that the metric is completely empty of any physical meaning, right? That's exactly the point, that you can have these evolutions into a singularity. For example, you can have this neck pinch singularity. So it's not true that you can, everywhere you choose to in space-time, always gauge away the metric to make it into a flat metric. That is possible only in outside of singularities and only at the shortest distances once you start losing the information about the curvature of the geometry itself. So yes, generically, in a generic point, the short distance behavior gives you just a flat metric and everything else was washed away as a topological gauge non-invariant degree of freedom. But then there are singularities like the neck pinch or the collapse of the sphere when the entire sphere goes extinct. And those singularities are the interesting features where zooming in on the short distance behavior does not give you a flat space. So the metric in that case carries that non-trivial information. So I can imagine having some probes of how many different singularities you encounter during some particular Ritchie flow from some initial configuration. You set up the initial configuration and the observables will have to do with the locations and the features of the singularities that the flow develops. And
but
those are the observables that are carried by the metric, but the probes of those observables would probably be, best probes would be extended objects wrapping around the singularities.
But just to be clear, that's not a statement about the topological nature of this theory, right? That's a statement about the gauge symmetry in this theory. So that's no different from Yang-Mills theory, right?
Yeah, I'm never sure what is semantics and what's the real physics or mathematics. If we say topological symmetry, what do we mean, right? I'm not sure.
Well, like in Yang-Mills theory, you might say that there aren't local observables because you should be talking about Wilson loops. But is that the sense here in which the metric is?
You can have composite singlet operators in Yang-Mills. Here it's more difficult because here it looks like all the local structure outside of singularities has been washed away completely. And that's consistent with the fact that there are no cohomology classes in the naive BRST cohomology of the field theory itself until you start putting in these extended observables. And whether that's a consequence of quote unquote being topological or having a gauge symmetry that happens to act topologically, to me, that's almost on the semantics side. I would say there is a symmetry that the theory has, which is locally in any local patch, arbitrary deformations of the metric are the gauge symmetry. And you can call it a topological symmetry and study whatever consequences of that gauge symmetry you find. You can call them topological. But to somebody else, topological might mean in the back of their mind that they want a complete independence of a space-time metric. And that's, of course, not what you get here. You get these residual features of the metric itself. And yet the theory is topological in the sense of not having local degrees of freedom and not having local structure in smooth patches of space-time.
I guess, so the way to think about it, I mean, a way to think about your theory is as a supersymmetric quantum mechanics, right? On a target space, which is the space of metrics on on a d-dimensional manifold plus.
That's right.
That's right. And I guess from that perspective, it's topological in two different senses. One, in the sense that the supersymmetric quantum mechanics is topological.
Absolutely.
In a 0 + 1 dimensional sense.
Yes.
Sorry. And then in the other sense, topological, that you integrate over the metrics. So it's topological because you integrate over all the metrics on the space. So, but there are two very different senses of being topological, both which are true.
That's why I'm never clear about what's semantics and what's a different usage of the same word topological in different settings, because I can think of at least 3 different meanings in which this theory is topological, right? So there's also the fact that you have this local deformation symmetry as a gauge symmetry, and it acts on the underlying geometric field in the spatial slices. So
I think, but by now, these, especially maybe Witten's work over the last 10 years or so, has sort of reminded us of those classes of theories. It's basically Floor type theories, which are supersymmetric quantum mechanics with exotic target spaces.
Yeah, it looks like it all has very similar origins, all the way back to the original Morse theory interpretation of this floor type theories and original Yang-Mills. That's actually another intriguing open question here, because it looks like superficially, to me at least, I don't see any discussion in the literature of trying to compare how the Ricci flow equations look like instanton equations in Yang-Mills. But there seems to be a close connection. In some sense, it is like rewriting Yang-Mills instanton equations in an artificial 3+1 split, and then interpreting them as a time evolution of some spatial connection controlled by the variation of the Chern-Simons action, which is the analog of the superpotential. Except here, the instantons sometimes don't live forever. Sometimes they end up in a singularity in some finite amount of time, and then you have to reglue another instanton and continue in the future, like in some Morse field theory argument. So I feel like this connection with Morse theory and Floor cohomology, this middle dimension cohomology kind of argument, could lead to some really interesting surprises here as well. That there are some features of that story that seem to be present.
I guess the one difference is that in Floor theory and Morse theory, usually you have lots of critical points. And here, you don't have that many critical points, right?
Right. And you have to kind of reglue these segments so you don't travel from a critical point to a critical point, but you allow yourself to cut this flow and reglue different segments of the flow. But again, this is way too intuitive. I don't really have any good sense how to put my finger correctly on whether this makes formal sense. But there's that feel that some parts of that story connecting to Morse theory should be accessible here somehow. So if anyone has any insights from the audience on this now or in the future, this would be very much appreciated. I think there is some real possibility for some non-trivial, interesting progress on both sides.
Are there some questions here where you can help the mathematicians out with? What are the big questions that
yeah, I would have to ask. I've been too modest so far, so I'm not offering this as a super powerful tool. I don't know of any really good immediate application, but perhaps finding some physically motivated ways how to bring this closer to Morse theory ideas, that might be one possible unexpected feature that would come from the physics motivation, simply because we are aware of how close this structure is to the conventional Yang-Mills instanton picture. Once you get over the details, then the essence is very parallel, and there should be some mileage that one can get out of it that might not be visible directly on the mathematical side. But I'm not sure. I defer to the mathematicians to judge whether this can be useful for them. So far, they have done such an amazing effort over the past 20 years, pushing the story in various dimensions, not just 3+1. Then there's also Kähler Ricci flows in 4+1, many other topics. They've accumulated so much data that we can spend decades probably just mining that for some implications for the physics path integral.
Sorry, question for the Morse picture. What do the critical, just a naive question, what do the critical points look like in this story?
Well, if I knew the answer to that, then there would be already a paper on this subject. We've spent some months thinking about this, and it feels like you're moving in a dark room. We feel like there are some details that are hopefully combining into some big picture, but until somebody turns on the light, you don't know what the big picture is. So I feel like I'm at the stage before somebody turned on the light. So I can't really answer that question, especially since, as I was saying earlier, in standard instantons, you flow from minus to plus infinity. If you look at the instanton in this conventional setting of splitting it into a 3+1 evolution, you flow from one fixed point to another. The instanton spans naturally this entire range. And here it looks like, unless there is some clever way of redefining, rescaling time in some different way than what we've seen, these instantons predict, to the extent that we can kind of propose them as being analogs of instantons, sometimes they terminate in a finite time and you can replace them with another structure. So the closest what I've seen in the math literature to this is this notion of Morse field theory that Cohen at Stanford and others have been pushing over the 15, 20 years. And that story seems to have similar ingredients, that you build kind of Feynman diagrams out of chunks of these flows, which don't necessarily have to go from one critical point to another critical point, or be tied together by one global Morse function. But again, I'm just speculating. I'm not an expert on that side. I'm happy to play with my simple physics path integral and see whether somebody can help sort this out and see if there's a deeper connection.
Thank you.
You emphasized at multiple points that Hamilton's equation couldn't be attained from a Lagrangian. Is the new ingredient that the point just that adding fermions is what allows you to do that?
No, for the Hamilton equation itself, it's not the fermions. Well, it is the fermions in the sense that if you don't have the fermions, then you don't end up with the localization. It's the supersymmetry structure and the localization principle here that boils down the path integral not just to naive solutions of classical equations of motion that you can write down, but only a very special subclass of classical equations of motion, namely those that are associated with the analog of the instanton equation. So we don't get the equation of motion of this system to be the Ritchie flow, Hamilton or Perelman. Equations of motion of this system, if you look at the bosonic equations of motion of the metric, then they would be of second order in time derivatives, and they would be of fourth order in spatial derivatives. And they can factor into essentially what would be analogous to the BPS and anti-BPS, whereas instanton and anti-instanton lower order differential equation. So That's how we get the Hamilton equation as a localization equation. So it's the analog of the BPS condition from physics rather than an equation of motion. And the same is true then for Perelman, but for Perelman, it wasn't surprising that there is a connection to a variational principle because that's how Perelman derived his system of equations in the first place. But for Hamilton, that was always in the literature that it is frustrating that we cannot derive it from a variational principle. So that stays true, but we can at least derive it as an honest localization equation in some path integral of just a spatial metric theory. We don't need the lapse and shift. We can just do it for the spatial metric, no gauge symmetry besides the topological symmetry, and the localization equation for specific values of the coupling constants is precisely Hamilton's flow equation. I think I saw a raised hand earlier.
Yes. If you speak about Hamilton, I know you speak about Perelman, and but I think of the equation, the expression GI J, and I remember this is has to do with Rowan Hamilton, and you can have also a quaternionic expression of this term, and so this would be four-dimensional. So I did not understand the point how Perelman solution of the Poincare conjecture could actually happen in a 3D interpretation. Can you explain how it
what do you mean by the 3D interpretation? I'm not sure what you mean by a 3D interpretation. I mean, I thought that the case of most direct interest for Perelman was three-dimensional Riemannian manifolds. And in order to prove the Poincare conjecture and the uniformization, or sorry, the geometrization theorem of Thurston, that's exactly how he designed the Ritchie flow in 3+1 dimensions to attack that problem.
Yes, but this seems to me the problem, because if you look at Rowan Hamilton's definition of time, then it's in the fourth dimension, and the Ritchie factor is actually also it's possible to express the Ritchie factor as quaternionic.
I'm not sure I know much about that, so I don't think I can comment.
So I'm puzzled, but I find very fascinating points. Like, what is super time? What are the three factors of your super time, if I may ask, please?
Yeah, this is exactly what Mina has been commenting on, that this theory is really just a 0+1 dimensional quantum mechanics. So the object that gets supersymmetrized naturally is the time dimension. And therefore it's promoted to what we call super time, which is just a fancy catchphrase for a 1/2 dimensional supermanifold, because we have two anti-commuting real superspace variables, and they do the translations satisfy the standard superalgebra of n equals 2 quantum mechanics, supersymmetry quantum mechanics. And then space is basically just an observer, a bunch of degrees of freedom that reside on the spatial slice. They just go on for a ride from the point of view of this supersymmetrization. There is no supersymmetrization of space in any sense. So just to make sure that people don't get the false impression that somehow we are supersymmetrizing the entire space-time, we call it super time to distinguish it from superspace.
Thank you. But this is the point, because I is the imaginary factor in the GI expression, which is then automatically leading to the fourth dimension in the original Hamilton.
I should say all our path integrals are in imaginary time. So there is e to the minus s in the action. There is no factor of I, just to be clear that this is really analogous to doing Yang-Mills in Euclidean signature, if you want to run that analogy with topological Yang-Mills. And if you try to recrotate to real time to get back into imaginary numbers, then this would be perhaps some kind of a physical theory with propagating non-relativistic gravitons, but nobody has been able to understand that theory.
Thank you.
Sure. I see I didn't do a very good job monitoring the chat, so I apologize for that. I'll read it in my... I think some of them have already been answered. And, again, I invite everyone who has any follow-up questions or any suggestions or any comments to email me, and I'm happy to discuss, or we can even set up Zoom meetings or something. But I guess people are already over-Zoomed. But by email, we can certainly, I'm happy to answer any follow-up questions that we weren't able to get to during the talk.
Just a quick question about the Morse theory picture again. You had the picture where instead of pinching, they go on to infinity, right? After some rescaling.
Well, again, depends on which exact environment you're asking about. I was just saying that in the conventional case where you are going from one critical point to another critical point through an instanton, then from the internal point of view of the instanton, this takes infinite amount of time. So intuitively speaking. And that's why that's an easier case compared to, for example, figure out what would be relevant here is some analog of a situation where you are happily moving along some instanton, thinking that you're solving the gravitational analog of that same problem, and all of a sudden you stop at some finite time and encounter a singularity. So then you have to decide what you were supposed to do at that point. And there are scenarios where you can start doing different such segments and maybe generalize Morse theory along those lines. But again, I'm not a Morse theory person, so I only have a very kind of an outsider perspective on this. But those are some of the features that seem to be built into this theory, that if we want to make sense of it as being analogous to Yang-Mills closer than so far, you want to be really rewriting the Perelman equations as being analogous to instanton equations, then there are many exciting, interesting questions. For example, what would be the analog of the Yang-Mills internal cage group? We of course know that in many cases you can massage gravity theories to look more like Yang-Mills, for example, in three-dimensional Chern-Simons rewritings of gravity. There are typically some non-compact gauge groups that you can use, and you can use the fact that the Yang-Mills equations of motion are on-shell equivalent to the gravity equations, or diffeomorphisms and Yang-Mills gauge theories are on-shell equivalent only in that specific dimension. You can use that feature. It looks like that part of the story, if it exists, would have to be figured out here if we want to make a closer match. But some of the ingredients seem surprisingly there. Like if you try to see, is there a possible parallel story? And the answer could have been no, but it's more subtle than that. There are some ingredients that seem to look very similar, except you would require some kind of a generalization that I'm not aware how to develop or whether it exists in the literature.
Okay.
Okay, Petr, thank you so much for
for
wonderful talk. I'm sure that this is just the beginning of the story.
I hope so.
Maybe not. Maybe it's somewhat analogous to when Witten wrote his paper on topological quantum field theory. He interpreted Donaldson's work, and that was not by any means the end of the story. It was just the very beginning of the story, right?
Right.
So
thank you for your kind remarks. This is a very optimistic point of view, and I appreciate that. Let's see what happens after this. So thanks again, everyone, for your patience. Sorry for being 1 hour overtime compared to the usual 1 hour.
You're actually not. This is our normal time. So thanks, Petr.
That's great. All right. Thanks, everyone. Stay safe.
Okay. Bye-bye.
Bye.